Hi, my name is Liang. I'll be presenting this work titled Pullback Geometry of Persistent Homology Encoding. This is joint work with Renata Turkeš, Jiayi, Otter, and Guido Montúfar. So, what is persistent homology? Persistent homology is an approach to create data representations based on the information about topological hosts. The basic idea under persistent homology is to first construct a filtration on the data, which is a sequence of topological spaces that approximates the data at different scales, and then to store the scales where those hosts first appear and disappear in the filtration. In this work, we focus on the encoding mapping from data to a persistence image, which is one type of vectorized pH representation. Given these pH encodings and a dataset, we aim to address these three key questions. First, how to measure the sensitivity of the encoding to a given perturbation, such as shearing and adding noises. Second, how to measure the effectiveness of the encoding in detecting a given data feature, such as a binary cat or dog label. Then, how to select the parameters for pH encodings for a given task. This would include the choice of filtrations and parameters for persistence images. A common solution to these problems is to employ a regression model or a classifier on top of the data representation and test its performance. However, such methods would lead to conclusions that are heavily contingent on the choice of the models and their parameters. In contrast, our method allows obtaining intrinsic insights to these questions without the need to train and select downstream models. Now, let me give you an overview of our methodology. First, we use tangent vector fields on data manifold to conceptualize data variations, and especially we're interested in two types of tangent vector fields. The first type are those introduced by perturbations on the data, such as shearing, and we call them perturbation vector fields. And the second type are the gradient vector fields of data features. Then we use the structure of the Jacobian of the encoding map to analyze the behavior of the encoding in response to those data variations. More precisely, the rank of the Jacobian would tell us the number of independent data variations that are captured by the encoding, while the eigenvectors of the Jacobian would describe the most and least important information that are captured by the encoding. And at last, the average pullback norm of a tangent vector field can quantify the sensitivity of the encoding to the corresponding data variation. Then one can select the pH encoding based on this information and on the specific practical scenario. To demonstrate how our method works, we first look at a synthetic dataset, the radial frequency pattern dataset. This dataset consists of point clouds sampled from shapes like petals. And on this dataset, we consider pH encodings constructed on different filtrations, and also a pre-trained point net encoding, which is a neural network architecture for point cloud data. By looking at the spectrum of the Jacobian of these encodings, we found that these Jacobians tend to have a low-rank structure, which means that this encoding only captures a small set of data variation. Then we evaluate the average pullback norm of 8 types of perturbation vector fields for these 4 encodings, and we observe that the information obtained by pullback norms aligns well with the existing understanding of persistent homology. For example, the pH encoding constructed on Vittori strips filtration and DTM filtration would completely ignore information about rotation and translation. And in contrast, the pH encoding on height filtration can clearly recognize Euclidean motion. These observations are consistent with how these filtrations are designed. Next, we shift our focus from perturbations to data features, and we show how our method can be used to select parameters for persistence images. We consider a real-world dataset that consists of point clouds sampled from ring Otter trees. Each point cloud in this dataset has a classification sex label. So with different choices of PI parameters, we evaluate the pullback norm of the gradient vector field of this sex feature. And meanwhile, we evaluate the performance of a logistic regression model to predict this feature. We found that there is a strong correlation between the pullback norm and the downstream task performance of the logistic regression model. Therefore, in practice, if we want to have an encoding that best captures a certain data feature, we can simply choose the encoding that achieves maximal pullback norm of the gradient vector field. This would eliminate the time and effort to choose a downstream classifier and tune their parameters. Finally, we focus on the weighting functions for persistence images. We'll introduce the beta weighting functions as shown in the slides. This type of weighting function can enable us to highlight persistence intervals with different length by tuning the mean parameters for the weighting function. So for different choices of the mean parameter, we evaluate the pullback norm of the gradient vector field of the sex feature, as well as the performance of the logistic regression model. We again observe a strong correlation between these two quantities. And more interestingly, we observe that persistence intervals with medium length are crucial in this task. This observation goes against the popular belief that long intervals are the most important, and at the same time, this confirms the finding from the original paper. In conclusion, the spectrum and eigenvectors of the Jacobian would characterize the amount of data variation and the most important data variation that are captured by the encoding, and meanwhile, the average pullback norm of tangent vector fields would measure the ability of PHA encoding to capture a given perturbation or a given data feature. And in turn, this quantity can help us to assess the ability of the pH representation for a downstream task. One limitation of our work is that all the analysis is based on the structure of Jacobian, so currently we're only looking at local data variations. In the future, it would be interesting to extend the method to non-local data variations. Furthermore, it could be also very interesting to obtain a finer-grained analysis on the gram matrix of the pH encoding, such as the property of its spectrum. So, thank you for listening.